So there's some algebraic properties of logarithms that I'm just going to write out now. So in a previous video, I mentioned the fact that b to the x plus y is the same as b to the x times b to the y. So in the reverse direction, what you get is that if you have the logarithm of a times b, that becomes the logarithm of a plus the logarithm of b. And this can be base whatever. So yeah, all these logarithm properties I'm going to mention work in any base. I just forget to write the base half the time. And so similarly, since b to the x minus y is b to the x over b to the y, then if you've got the log base b of a divided by b, that's going to be the log of a minus the log of b. And the last one is, remember that b b to the x to the y equals b to the x times y. This corresponds to, if you've got log base b of a raised to the bth power, you can take this exponent and you can pull it in front of the logarithm as a coefficient. And so just to demonstrate that, so that tells me if I have something like the log of 6 should be the log of 2 plus the log of 3. And I can just demonstrate that really quickly. Log of 6 is that, log of 2 is that, log of 3 is that. If you do log 2 plus log 3, you in fact get log of 6. And so then obviously if you subtract log 6 and log 3, you get log 2, which is log of 6 over 3. So these two rules are reverses of each other basically. But the cool one is, suppose I give you the log of 9. That should equal twice the log of 3. What's log 9? And in fact, if you look at that, 2 times the log of 3 is the log of 9. So what can I use this for? So I can use this if I have expressions like log base 3 of a times b squared over c to the third, I can do what's called expanding this. So there's a quotient here. And so I know from up here that the log of a over b is log a minus log b. So this becomes the log base 3 of a times b squared minus the log base 3 of c to the third. And I know that if you've got a product inside a logarithm, you can switch it to a sum of logarithms like this. So log of a times b squared is log of a plus log of b squared. And the last thing I can do is I can pull those exponents out in front. And so in that way, I can expand these logarithmic expressions. And this is something that can be useful when we do calculus with these things. On the other hand, if I give you an expression like log base 5 of x plus 1 plus twice log base 5 of x minus 3, I can reverse the process. I've got this 2 outside, so I can pull that in as an exponent. So it becomes the log of x plus 1 plus the log of x minus 3 squared. And since these are added, this whole thing becomes the log base 5 of x plus 1 times x minus 3 quantity squared. And so you can use this process in order to solve equations. Like theoretically, I could have said, like 5 equals this. And so then you get 5 equals this, and so you get 5 equals this. And so then, if 5 is the log base 5 of this, I can take this and I can write it in exponential form. And that gives me that 5 to the 5th is equal to x plus 1 times x minus 3 quantity squared. And so now this is a polynomial equation. It's an awful polynomial equation, but it's a polynomial equation that you could theoretically solve. How long have I been going? Right. I'm going to do one more example of each. So suppose I have the natural logarithm of the square root of x squared plus 7x plus 12. All right, so the first thing to notice is this is the natural logarithm of, remember the square root of something is its 1/2 power. Right? So that means I can pull the 1/2 out, and I've got 1/2 the natural logarithm of x squared plus 7x plus 12. But x squared plus 7x plus 12 factors. It's equal to x plus 3 times x plus 4, because 3 times 4 is 12, and 3 plus 4 is 7. So this is then 1/2 of the natural logarithm of x plus 3 plus the natural logarithm of x plus 4. And so you can actually rewrite the whole thing as the natural logarithm of x plus 3 plus the natural logarithm of x plus 4, all divided by 2. And in the other direction, suppose I give you the log of a plus 3 times the log of b minus 4 log c minus log of d. So the first thing I'm going to notice is I can pull these coefficients in as powers. So this is log of a plus log of b cubed minus log of c to the 4th minus log of d. The next thing that's not quite so obvious to do here is this is log a plus log of b cubed, but then since these are both subtracted, this is minus the log of c4th plus the log of d. I can distribute the negative sign out. That's helpful because I'm adding these two logarithms together, and so this becomes the log of ab cubed minus, this is the log of c to the 4th d. Since I'm adding them inside the parentheses, I can multiply the insides of the logarithm function. And then lastly, I'm now subtracting two logarithms, so I can make a fraction where the numerator is the first thing and the denominator is the inside of the thing I'm subtracting. And so then I'll just put parentheses around this for clarity, and that is how we can simplify and expand logarithmic expressions. All right, so next I'm going to talk a little bit about how we can use all of this to solve logarithmic and exponential equations.